Hello and welcome to this video on momentum. Specifically today we're going to be talking about graphs and how we can use them to interpret momentum and make some calculations. These graphs were generated using a lab setup with a track like so, and on either end a motion sensor. The two carts were placed on the track then, like so, and then set to collide into each other. In this one we can gather a lot of information. For instance, if we look from this point on, we can see that there was an initial push to the red car, which gave it an initial velocity and some initial momentum. And then at this point here, there was a collision, which caused a transfer of momentum. There are several things we can conclude here. Let's take them one at a time. First, we can conclude that the blue car was at rest initially, because it has no change in position and no change of velocity. We can also conclude that the collision happened here, because that's where the velocity of both the red cart and the blue cart occurred. We can look at the slopes of these two, or their velocity values, and see that the red car had a velocity of roughly 0.2 meters per second, and the blue car had a velocity of roughly 0.2 meters per second, which tells me that the carts were heading at the same velocity, which likely indicates that they were stuck together. But possibly the most useful pieces of information come from right here to right here. The change in velocity. Because change in velocity is directly related to change in momentum, if we know, let's say, the mass of the red cart, we could calculate the change in momentum for the red car. In this case, it goes from 0.42 to 0.2, or change delta V equals 0.22, which means if I know the mass, which I do, it's half a kilogram or 500 grams, my delta P is 0.11. I can also look to see how much momentum the other cart gained. In this case, the amount of momentum lost, the difference between these 2 points, are the same. The amount of momentum lost by the first car is gained by the second car, telling me that there is conservation of momentum going on. Further, the fact that the change in velocity is the same, and I know momentum is being conserved, tells me that the carts have the same mass, or approximately, because of how that transfers. In order for them to both have the same velocity at the end, or more correctly, in order for the velocity lost here to be equal to the amount gained here, they would have to have the same amount of mass in the collision. Finally, I know for a fact, based on the difference in velocity, that this is a perfectly inelastic collision because the slope values here, or the velocity values here, are the same magnitude. Because of how the sensors are set up, they won't be the same value, but they're the same magnitude. There are so many possible calculations we can make here, so many different things we can look at. There's just so many potential options. To make it a little easier on you, for some examples, let's go to a simpler problem. In this case, it's the same setup as before, with a cart and track, only in this case the red car isn't moving. How do we know? Well, in the position time graph, the red line doesn't move. Its velocity is 0 almost everywhere, except for this little divot right here. The value for the second graph does change. In this graph, is the momentum being conserved? Yes or no? And how do we know? Well, if we look, we go from having positive to negative velocity and no change here, which indicates to me that momentum isn't conserved because the direction matters. There is a collision going on, there is impulse occurring. We can see it here a little more clearly, positive to negative velocity, and there's no gain. This is a collision where there's no momentum being conserved. There is impulse going on. And we can find that via our slopes. So let's recap. First, if we have two objects moving, we can see whether or not momentum is being conserved by the changes in velocities, provided we know the masses or that the masses are the same. We can see exactly how much velocity is lost and calculate our delta P if we know our mass. If there is velocity change, but there is no gain elsewhere, we know we're dealing with a situation where impulse is being provided. In this case, the red cart was held still as the blue cart bounced off of it. Which takes me to my final point, being able to measure or calculate different values. Here we could calculate our initial momentum if we could find the slope, For reference, this is right here, 0.5 meters per second, and down here is 0.4 meters per second. So let's talk about our carts. Our carts in the lab are 515 grams exactly, which is 0.515 kilograms. Calculate the impulse. Go ahead, give it a try, check back after you're done. To start, I lied a little bit. This isn't 0.4, it's negative 0.4. You should be able to infer that from the graph, but if you didn't, that's okay, just my mistake. Secondly, once I got that, I can write down my entire impulse equation. Impulse equals force times time, which is equal to delta P, which is m times delta V. I use the last one because the mass of the cart isn't changing. All I need to do is calculate my delta V, final minus initial. And you should get negative 4.635 newton second. The other way we can go about calculating impulse from a graph is if we have a force versus time graph. We defined impulse to be J equals F times delta T. Typically when you see this, this means average force at the algebra level we're at, but we could also calculate the total varying force using an integral. Or we can use the old trick of taking the area under the curve. This graph is force versus time, so force times time. All I need to do is take the area of this impulse provided to an object, and I'll be able to calculate the value. So in this case, the triangle is 1, 2, 3, 4 seconds wide, 1, 2, 3, 4 newtons tall. So the force would be equal to the area, which for a triangle is 1/2 times base times height, which is 1/2 times 4 seconds times 4 newtons, or 8 newtons seconds. To summarize, once again, there are two different graphs you can get impulse from. One is a velocity graph if you look at the changes in velocity and know the mass. The second is from a force time graph by looking at the area under the curve. Anyways, thanks for watching. Have a good one.